All right, so good morning, everyone. Uh, so this is the second part of your second lecture, which is the fundamental of digital electronics. So in the previous class, we have discussed some of the basics of digital electronics. We have discussed about the logic gates. We have also discussed about combinational circuit. So combinational circuit, they are basically combination of logic gate. So you connect different logic gates according to your output which you want to get your output, right? And then we also discussed like how we can simplify the Boolean expression, right, to get the same output. So very often we connect a large number of gates, right? So which are unnecessary. We can produce the same output with less number of gate. So there are two methods which we have discussed. We have discussed about Boolean functions, right? Those algebra, those formulas which we can use, right, to reduce the Boolean function. And the second method is K-map, right, Carnot map, which we can use, which is a pictorial representation. So using some picture or some tables, we can reduce the Boolean function. Now, logic circuits, they are of two types, as I've mentioned in the previous class. One of them we have discussed. We have discussed about the combinational circuit. Now, the second type of logic circuit is your sequential logic circuit, right? So in the case of sequential logic circuit, you have the combinational circuit. Along with that, you have the memory element, right? So what this memory element will do is it will store the output, the previous output, okay? It will store the previous output and then feed it back to the input of your combinational circuit, right? So in the case of sequential logic circuit, the current output, this output, the current output, it will depend on the current input plus your status of your memory or your previous output, right? So that is a slight difference between your combinational circuit and sequential circuit, right? So in the case of sequential circuit, your output, your current output or present output, it will depend on your present input and the previous output, because that has been stored in the memory, right? So sequential circuit is combinational circuit with memory element, right? This one. So therefore its output depend on current input and the previous output stored in the memory element. Okay. Now we have already discussed about combinational circuit. We know what it is, but we don't know about the memory element. Okay, how they store. So let's talk a little bit about the memories in sequential circuit. So memories in sequential circuit, they are of two types. You have latches and flip-flop. Okay, so latches, they are the building block of flip-flop. Latches are the building block of flip-flop. So latches are the basic memory element, right? And using latches, we can develop flip-flops. Okay, so latches basically, they can maintain a binary state or they can store the binary state. Binary state means In binary you could have only two states, either 0 or 1, right? Only two states are possible. So this binary state, it means either 0 or 1. So it can store the binary state indefinitely, okay, as long as your input signal does not change. So latches, they can store binary state as long as input does not change. Okay, so if you change your input to produce a different output, then that output can be saved. Okay, so latches, they can store the binary state as long as your input is not changing. And latches, they are the building blocks, or they are the most basic element using which you can develop a flip-flop. So latches are the building blocks of flip-flop. Okay, and storage element, so latches are storage element that operates on signal level. So if input level changes, output changes. So we have already discussed that. Okay, so if you change your input, your output will change immediately. Now in the case of flip-flop, so again using latches we build flip-flops, right? So they are again binary storage devices which can store 1 bit of information. Okay. However, in the case of latches, they operate synchronously, in a synchronous manner. Okay. So what happens is, in the case of flip-flop, along with your input, you also have to provide a clock pulse. Okay. So until and unless the clock pulse is high, your output, not height, high, your output will not change, right? So if the clock pulse is low, the output will not change. Okay, in the case of flip-flop, right? So clock pulse is basically simply your signal generator which generate square waveform, right? So if your signal is high, it would signify 1. If it is low, it would signify 0, right? So in the case of flip-flop, only when the clock pulse is high, the output will change. Okay, so even if your input is changing and the clock pulse is low, the flip-flop will have to wait until the clock pulse become high. Okay, then only your output will change, right? So it happens in a synchronous manner. In the case of latch, as soon as you change your input, the output will change. But in flip-flop, the memory element or your flip-flop has to wait until your clock pulse become high. Okay, so slight difference over there between latch and flip-flop. Now there are several types of latches. So since latches are the building block of flip-flop. So let's first try and understand latches, and then we will move forward and study about flip-flops. Okay. So latches, they are of several types. So this latch over here, it is made out of two NOR gates. Okay. So we can say that this latch is made out of cross coupled NOR gates. So cross coupled means you can see the output of one flip-flop is connected to the input of one flip-flop, and then again the output of this flip-flop is connected to the input of another flip-flop. So they are cross connected. Okay, cross connected or cross coupled NOR gates. Now this latch is called as set reset, or in short SR latch. Okay, so a latch is said to be in set mode when your output Q is equal to 1. Okay, and it is said to be in reset mode when your output Q, the same output Q, is 0. Okay, so in this SR latch, you could see you have two inputs, S and R, and you have two outputs, Q and Q dash. Okay, so output Q is your output that we are monitoring, and Q dash is complement. So Q dash is complement of Q output. Okay, so if Q output is 0, it should be Q dash will be 1, and if it is 1, it will be the complement or the opposite, it will be 0. Okay, so this is the basic construction of your SR latch. Okay, so what happens is in this SR latch, if you want to reset your latch, or let's say if you want to set your latch, okay, so set means the output Q should be 1, right? So what we have to do is we have to apply S equal to 1 and R equal to 0. So in that case, the output Q will be 1 and output Q dash will be 0. Okay, so this is said to be, now my latch will be in set mode. Okay, in the case of reset, so now if you want to operate your SR latch and you want to change the output, right, you want to reset, you want to operate it in reset mode. So in that case, the output R should be 1 and the output S should be 0. In this case, the input R should be 1 and the input S should be 0. In that case, the output Q will be 0 and Q dash will be 1. Okay. So S will be 0, R will be 1. Okay. Then your output Q will be 0. So it's quite simple. If you want to set your latch, in that case, S input should be 1 and R should be 0. If you want to reset, then R should be 1. Okay. So if you want to set, S input should be 1. If you want to reset, R input should be 1. Okay. And in that case, the output of set mode is 1 and the reset mode is 0. Okay. Now, so once you have set the output, you would like to store the output, right? So to store the output, we operate the latch in memory mode. So memory mode, it will store the output, or it will retain that output. Okay. So once you have set or reset your output, and then if you apply S equals to 0 and R equals to 0, then whatever is your output, if your output is 0, it will be stored. If your output is 1, it will be stored. That means no change in output. Okay. So in memory mode, no change in output. Okay. So whatever is your output, it will remain to be the same. Okay. So that's how we change the output and we store it. Okay. The last remaining case, that is this one, when S is equal to 1 and R is equal to 1. Okay. So in this case, this is forbidden, right? So you are not allowed to use it. Forbidden state or forbidden mode. This is not allowed to use. Why? Because if you look at the output Q is 0 and Q dash is also 0, which goes against our logic. We have built this circuit such that if your output Q is 0, output Q dash should be complement. It should be 1. Right? They should be opposite of each other. If Q is 1, the output Q dash should be 0. They should not be same. But here in this forbidden state or forbidden mode, both the output Q and Q dash, they are 0. So since it goes against the logic of our circuit, right? Both the output are coming out to be same, so we cannot use it. Okay. If you use it, your next output will be wrong. Okay. So that is why we cannot use forbidden state. Okay. So there are two problems in latch. in this SR latch. One is we cannot use forbidden state. Okay, so these are the problem, right? So this is one of the problem, and the second problem is your first input cannot be memory mode, right? My first input cannot be memory mode. That is S equals to 0 and R equals to 0. You cannot have this as your first input. Okay, so in the class notes I've explained the working of this flip-flop or this latch, right? If you are interested, you can go through it. I've also demonstrated what would happen if your first input is memory mode, right? How your further outputs will go wrong. Okay, quite simple and straightforward. But if you are interested, you can have a look at that. So these are the two basic problems, right? In your SR latch, right? We'll solve them in further latches. Okay, but before we go on to solving this problem, there is another type of SR latch, which is this one, which uses NAND gate. Okay, which uses two cross-coupled NAND gates. Okay, so in this case, it has the same set of problems. Everything is same, except the output are just the opposite. Outputs are just the opposite. So in the case of NOR gate, when we were using the previous circuit, in the case of NOR gate, if you want to set your latch, S input should be 1 and R should be 0, then your output Q will be 1. If you want to reset, your S input should be 0 and R input should be 1 and your output Q will be 0. So this was about NOR gate. Okay, but in the case of NAND gate, it is just the opposite. Okay, so output, so when S input is 1 and R is 0, in that case output Q is 0. So that means your latch is reset. When S input is 1, in the case of NAND gate, when S input is 1, your latch is reset. Okay. Now in the case of NOR gate, my memory was S equal to 0 and R equal to 0. Right. But here in this case, in the case of NAND gate, my memory mode is S equals to 1, R equal to 1. So that's my memory mode. Okay, just the opposite, right? Now if you want to set your latch, your S input should be 0 and R input should be 1, then your Q output is 1. So that means this is my set mode. Okay, so in the case of NAND gate, what we are observing is when your S input is 0, R is 1, then my Q output is 1, that is set mode. And my NAND gate SR latch, it is getting reset when S is equal to 1 and R is equal to 0. Then my output Q is becoming 0. So you can see, you can compare. It is just the opposite of what we were doing in the case of NOR gate. Okay. Otherwise, it's almost the same. The reason why I have discussed this NAND gate is because the two problems which I discussed, they will be solved using this NAND gate SR latch. Okay. So to solve one of the problem, what we do is we modify this SR latch. Okay. How do we modify? So this part is the same as the general or the previous circuit of SR latch which we have discussed. What we do is we add additional NAND gates, 2 additional NAND gates, right? And connect one of the inputs together and call it as C, right? And your 2 inputs, they are S and R. Along with that, you have a third input C. Now what happens is, until and unless your C input is 0, there will be no change in the output. You can change the output only when your C is 1. Okay. When your C is 1, only then you can either set or reset your latch. Okay. So when C is 1, when your C input is 1 and your S input is 0, okay, the first case, and your R input is also 0, you can see this is the memory mode. Right? The mode in which the latch stores the data. Okay. So even if your first input is 0, 0, right? So even if first input is S equals to 0, R is equal to 0, that means I'm operating the latch in memory mode. Then also this SR, this modified SR latch, it will work. Okay. In the previous case, the problem number 1 or one of the problem was that we cannot have S equals to 0, R equals to 0 as the first input. Okay. But in the case of modified SR latch, even if the first input is S equals to 0, R equals to 0, the latch will work. Okay, so you can have that input as your first input. Okay, then if we look at the reset state, so in that case what we have to do, we have to apply R equals to 1. Okay, so again we have kind of simplified one of the problem. In the NAND gate, it was coming out to be the opposite. But now after modifying, your latch will be reset when your R input is 1. Okay, so this is for modified SR latch. Okay, and your latch will be set to 1. Okay, reset means Q output is 0. Okay, and S is 0, and your latch is set when your S input is 1 and the output will be 1. Okay, so when your S input is 1 and R input is 0, your output Q will be 1. Okay, so to set the latch, S input should be 1, and to reset the latch, R input should be 1. Okay, right, so we have solved one of the problem, and we can use the memory mode as the first input. But again, one of the problem, the second problem, is still there, right? So in the second problem, this is your forbidden state. Forbidden state or forbidden mode, where output Q was coming out to be equal to Q dash, right? So this problem, this second problem is still there. Okay, it is, you still cannot use both S equals to 1 and R equals to 1, because in that case your output, both the output will come out to be equal, right? So still the second problem is there. Now we will do a little bit of modification again, right, to solve this problem. So the next type of latch, it is called as D latch. Okay, so it will solve both the problem. Both problems. Right, so in this latch, until, or in this dotted box, it is my modified SR latch. Yeah, along with that, what we have done is we have connected the two inputs, right? So we have connected the two inputs together, and now we have only single input, right? If you you have a single input, along with that you have your enable. Now we are calling it as enable pin, EN. Okay, so one of the input is connected through NOT gate. In the second problem that we have just discussed, what was happening? S is equal to 1 and R is equal to 1. So this was my forbidden, or we were restricted from using this input, right? But now what you can see is, if you apply 1, and since you have a NOT gate, your second input will be automatically 0, right? And if you change it to 0, your second input will be 1. So there will be no condition when both your inputs, they are same. right? So in D latch there will be no condition when S is equal to R, that is both your input they are same, because you have connected a NOT gate. Yeah, so it will solve kind of both of my problems. So let's quickly go through the working or this truth table. So now instead of C input, now we are calling it as enable input, right? So if enable input is 0, then you cannot change the output. Okay, so no change in the output. Your output will change only when enable pin is 1. Okay, so when enable pin is 1 and your D input is 0, when your enable pin is 1 and your D input is 0, the output Q will be 0. That is your reset state. Okay, and when your D input is 1, then your output Q will be also 1. That means your set state. So whatever is the input, the same will be the output in case of D latch. Okay, so your input is equal to output, provided enable pin is 1. Okay, D latch. Now instead of enabling the pin every time, so you apply a high pulse to the enable pin every time to enable the circuit or to operate the circuit. Instead of doing that, if we connect a clock pulse like that, right? So D latch can be used as flip-flop. Okay, so I have a better picture of this. So this D latch can be used as a flip-flop if you connect the enable pin with a clock pulse, right? So whenever your clock pulse is high, whenever your clock pulse is high or 1, your output will change according to your input. Yeah. So whenever your clock pulse is 1, if you have a 0, the output will become 0. And maybe at the next clock pulse, if it is 1, it will change to 1. Right? So now we can synchronize the D latch and make it work as a flip-flop. However, there is a problem. If you directly use D latch as a flip-flop, there is a problem. Okay. What is the problem? So the problem is, let me amplify this clock pulse. Okay, so let's say my clock pulse is high between 0 seconds to 1 second. Okay, so for entire 1 second my clock pulse is high, or it is 1. Okay, so during this entire 1 second or during this entire time period, the the output can change according to your input. Okay. Now, this flip-flop or this memory element is connected to a combinational circuit, if you remember. Okay. So this memory element or my flip-flop is connected to a combinational circuit, right? So if my clock pulse is high for, let's say, 1 second, so during that entire 1 second, the output of the memory element can change, and the output of this memory element is going back to the combinational circuit, to the input of combinational circuit. That means it will change the present output or your output of combinational circuit. Now, if your output can change during this entire period, then usually the logic circuit, they operate very fast. It will take a fraction of a second to process and generate a new output, right? So during this period, if the output changes again, then still, since the pulse is high, my memory will produce a new output, or you will have altogether a new output, right? So the problem with D flip-flop, if you directly use it, if you directly use D latch as a flip-flop, the problem is the output of memory can change throughout the time when clock pulse is high or it is 1. Right? It can change throughout that duration, throughout this time. Right? And generally your logic circuit, they operate very fast. So you can have your output will change continuously. Right? Instead, what we want is the memory should store whatever the output is. It should remain the same. It should not frequently change. It should not continuously change. Right? But if you use a D latch as a flip-flop, this is going to happen. Okay. So the same thing, I have explained it here in these text. You can read it. But the solution of this is what I am going to discuss next. So the solution of this is using two flip-flop, 2 D flip-flops. So this is the solution of the problem. So 2 flip-flops, they are used in master-slave configuration. Okay. So you can see you have 2 flip-flops in which the clock pulse, right? The input clock pulse is directly connected to your master flip-flop, and the second flip-flop or your slave flip-flop is connected through a NOT gate. Okay. So what will happen is when you apply, let's say your clock pulse is high. Okay. So in that case, the master flip-flop will be on, right? Because the clock pulse is high, and on means your output can change, right? But since you have a NOT gate connected, so it will inverse whatever the clock pulse is. So your slave flip-flop will be off. That means the output of your slave flip-flop cannot change, right? So if you, whatever is your input, let's say if it is 1, okay, so since your master flip-flop is on, the output Y will change, right? But your output Q will not change. Because your slave flip-flop is off, it is turned off. Okay. Now, when your clock pulse becomes 0, right? So in that case, your master flip-flop will become off, or it will turn off, right? And your slave flip-flop, it will turn on, right? So the output of your master flip-flop cannot change, but now your output of your slave flip-flop, it can change. So what will happen is, when your clock pulse becomes low or 0, your output Q will change according to the input Y, right? So what is happening is, if I try to represent it in the square wave, so when the square wave is high, output Y changes to 1, right? This output of master flip-flop. Now when this clock pulse is going down, right, to back to low level or 0, then my output Q is changing. Okay, so this is called as negative edge trigger. Negative edge triggered or negative edge flip-flop. Okay, this one. So similarly, you can have positive edge flip-flop. So basically what we try to do is, we try to change the output at the edge of the square waveform, not during the entire duration. Okay, so output is not changing, output is not changing during this entire duration, it is changing at this edge when the when your clock pulse is changing from 1 to 0. At this edge your output will change, right? So this will prevent further changes in the output, since you have a very short duration in which the output of your memory state is changing. So it's quite short, and we can use this to store the binary bits, right? So usually D flip-flop, they are operated in edge triggered, or we use edge triggered D flip-flop as a memory element. Okay, so this was all about your flip-flops. Analog to digital converter and digital to analog converter. Now we have already discussed what is a analog signal and what is a digital signal. So analog signals, they are continuous in time, okay, whereas digital signal, they have discrete value with respect to time. Now in most of the communication system, we need analog to digital conversion, and at the receiver side we need digital to analog conversion, right? So when you use your mobile phone to talk with someone, what happens is your voice is analog, right? It is a analog input. So your mobile phone, it will convert the analog signal into a digital signal and then send it to a nearby mobile tower, right? And then this mobile tower will send the signal to the receiver end, and at the receiver end, maybe if you are talking to your friend, so in your friend's mobile phone, that digital signal is then converted back into analog signal, that is voice, right? Again, right? So this analog to digital and digital to analog conversion is very frequently used in communication system. And in most of the avionics system, we will be using many of these ADC and DACs, right? So ADC stands for analog to digital conversion, and DAC, it stands for digital to analog conversion, okay? Now, along with the communication system, you will have many sensors, right? So air data sensors in avionics, which collects the temperature, the pressure of the surrounding air, right? And maybe some vibration in the body, or what is the velocity of the aircraft. So all those data, they are analog, right? Then you have sensors which will convert these analog signals into electrical signals, right? So again, those transducers, they do this process of analog to digital conversion. Now, one of the very common question would be, why do we need to convert the analog signal into digital signal, right? We talked about we use ADC for communication system, we convert the analog signal into digital. Even the sensors also, they would convert the analog signal into digital. But why do we need to do that? Why can't we use the analog signal itself? What is the problem? So usually analog signal, they are susceptible to noise, right? They can be affected by noise very easily, right? So that is one of the reasons why we cannot use analog signal directly. Whereas your digital signal, they are less susceptible or affected by noise. That is why we do analog to digital conversion. The second reason is difficult to process the analog signal in analog domain, right? So since your analog signal, it is continuous in time, right? That means it can have infinite number of values between any time period, right? So it is quite difficult to store that huge amount of data, and it is quite difficult to process that data, right? So that is why we cannot operate, or we cannot use the analog signal. We have to convert it into digital signal, right? So the last 2 points are what I have just mentioned. So digital signal, they are easy to process because you have less number of data, or you can handle that amount of data. So that is why in digital domain, if you want to process the data, it's easy. And again, you have less number of data, so it is easy to store that data. Okay. Now, analog to digital conversion. So for converting an analog signal into digital, we basically use two processes. The first step is to sample the data. So sampling means at regular interval of time, we take out some data from the analog signal, right? So let's say at every 1 second, we take some data from the analog signal, right, to make it discrete. So the ADC samples the analog input at discrete interval of time. The second step is quantization. So quantization is the process of assigning binary bit, or representing these samples with a binary number. Okay, so maybe you might be having, let's say, 1 volt. So this is represented as 001. Okay, now here if you say we have 2 volt, it will be represented by 002, like that. Okay, so we assign binary bits to the different voltage levels, or whatever the value you are calculating, whatever is your amplitude. Okay, so first we take discrete at every interval of time, we take the data and we convert it into binary. So those are the two steps which we use to convert analog signal into digital. Now the resolution of ADC, okay, it is given by this formula. It is equal to full scale range, or in short we call it FSR, and divided by 2 to the power n. Now n is your number of bits. Okay, so let's say if we take an example, so if we have a 3-bit ADC and the full scale range is 10 volts, and we are asked to calculate what is the resolution of this ADC. So we are given with the full scale range value, which is 10 volt. We are given with the number of bits that this ADC is using. So it is using 3 bits. So the value of n is 3. Okay, so we can write it as 10 divided by 2 to the power 3, and if you calculate it, it will come out to be 1.25 volt. Okay, so what it means is this is the minimum change in the input that can be detected by your ADC, right? So 1.25 volt is the minimum change in input which you can detect using this 3-bit ADC. Okay. Similar type of example. So in this case, the input to an ADC is in the range of 0 to 10 volts, right? So let's say your input is between 0 to 10 volts. Okay, then what is the resolution of a 8-bit ADC. So in this case, FSR value is not given, full scale range is not given, so we have to calculate. So full scale range, it can be calculated by this. So you subtract Vmax from, Vmax minus V minimum. So the maximum voltage which you are detecting is 10 volts and the minimum voltage is 0. Okay. So, and this is a 8-bit ADC, so number of bits will be 8, right? So you can write it like this. So 10 minus 0 divided by 2 to the power 8. And if you calculate it, it would come out to be 39 millivolt. So now what we can see is the minimum change in the input that can be detected by this 8-bit ADC is 39 millivolt. Okay, so in the two examples which I have given, we can see that by increasing the number of bits, so previously we used 3 bits, now we are using 8 bits, right? So by increasing the number of bits, the resolution can be increased, right? So if you want to detect very small signals, you should use large number of bits. Okay. Now the next thing is about sample and hold circuit. So as I mentioned, there are 2 steps of converting an analog signal into digital. You sample the signal, that means you take a sample of your data from the analog signal at a regular interval of time, right? And then you convert them into binary. So generally we assume that this process is synchronous, or it will happen automatically, right? You take the sample and it will immediately convert it into binary bits, or it will quantize the data. But practically it takes some time to generate the binary data, right? It does not happen immediately. So we need some kind of circuit to hold the sample, right? So we often use sample and hold circuit. So this circuit, what it will do is, it will sample the data and store it. Sample plus hold, or you can say store the data. And then one by one, it will provide this data or this sample to the quantizer, right, to convert the sampled data into binary, right? So very often we need this sample and hold circuit, because your quantizer or your quantization process is not very fast. Okay, so you have to hold, or you have to store the data, the samples, right? So if we want to develop an overall block diagram of your ADC, so it would include 2 blocks. You would have sample and hold, and your second block will be quantization. Okay, so this will sample the data at regular interval of time and hold this data, and then send it to your quantizer to convert it into binary number. Now, so we have talked about the transmitter side. So at the transmitter, you would convert the analog to digital, right? You would need a ADC. Now at the receiver side, you would need to convert it back, right? That is digital to analog conversion. So there are two types of DAC. In short, we call it So in short, we call it DAC. Okay, digital to analog conversion. So in the figure, in this slide, you could see that you have a 4-bit DAC. Right? So you have A, B, C, D. You have 4 bits. Right? Now, corresponding to the binary input, each of these inputs A, B, C, D, they can either have 0 volt or 5 volt. So if your input is 0, or if you have one of the input as 0, then the corresponding input should be 0 volt. And if the input is 1, if the binary input is 1, then you should have 5 volt at that input. Okay. Now, so if you have any binary digit, let's say 1001, like that, or let's say this one. So in this case, the last bit is called as least significant bit, LSB. Okay. And the first bit is called as most significant bit, MSB. Okay. So least significant bit is applied to A input and most significant bit is applied to D input. Okay. Then you have some resistors which are connected. You have these resistors of different value, 1 kilo ohm, 2 kilo ohm, 4 kilo ohm and 8 kilo ohm. So these resistors, they are going to attenuate your input voltage, right? So the voltage at A input, it will be attenuated by 1 divided by 8, right? So that resistor will reduce the voltage. Okay. And your B input, it will be attenuated by 1 by 4. Right. Similarly, your C input, it will be attenuated by 1 by 2. Okay. Whatever the voltage is, maybe 0 volt or 5 volt, it will be attenuated half of it. Right. Similarly, the most significant bit or the voltage at D input, it is not attenuated, right? Its voltage is not changed, right? So this is how all these data or all these voltages will be attenuated. Now they are added together by this op-amp. Okay, this operational amplifier will add all the voltages which are coming from this side. Okay, so I've taken an example of a 4-bit binary number. Let's say my binary input is 1010, right? So correspondingly, this will be my LSB and this will be my MSB. Okay, so this will be VA, then this will be the input at VB, and this will be the input at VC, and this will be VD. Okay, so if you have 0, that means you should have 0 volt, and if you have 1 as a binary number, you should have 5 volts, right? So correspondingly, VA will be 0 volt and VC will be 0 volt. Okay, whereas VB and VD will be 5 volt because they are 1, right? And if you use this formula and apply and do the calculation, you would get 6.25 volt as your analog output, right? So 6.25 volt will be your analog output. Now you have a negative sign here, right? So it doesn't mean anything. Basically, we should not be concerned about that. It only means that your op-amp is operating in as a inverting amplifier. Right? So it kind of invert the output. Right? So at the output, we can ignore this negative sign. It happens because of your op-amp. Right? So basically your analog output will be 6.25. Okay. Now, next type of digital to analog converter is your R to R ladder, and this is important. Okay, so R to R ladder. Now in the previous case, in the 4-bit DAC, we have to use 4 precisely controlled resistors, right? For digital to analog conversion, in the previous case, in this case, these 4 resistors, right, should be precise. It should be very accurate, right? And the second problem in this circuit was that the difference between the 2 resistors, right, the difference between the 2 resistors, they are quite high. One is 1 kilo ohm, then the next resistor is 2 kilo ohm, double of that, and then again double of that, you have 4 kilo ohm, and then again you have twice or double of it is 8 kilo ohm. So there was a difference quite a lot. The difference was very quite a lot. Okay. So in this case, what we do is we use only 2 resistors, right? One is R and another is 2R. So using only 2 precisely controlled or precise value of resistors, we can build this circuit. Okay. Now, in this case, basically this R to R ladder, it improves the accuracy. Okay, so that is why this R to R ladder is preferred in comparison to the previous DAC which we have discussed. So to improve the accuracy, we must have resistance with smaller difference. Okay, so we use this R to R ladder which uses resistance which are quite close to each other, right? One is R and another is 2R. Now the current input, this one, sorry, the current output, I out, it will depend on the position of these switches, these 4 switches. Okay, and the switches, they can be controlled according to the binary input. So if your binary input is 0, this switch will be connected to the ground, right? And if your binary input is 1, then the switch will be connected to this V reference. Okay, so you can control, or basically the connection of these switches, they are controlled according to the binary input. Okay, now depending on the binary input, either you will have V reference or it will be 0 volt. Okay, so all these voltages, they will be added together, right? So you will get some current I out, which is flowing through this op-amp. Again, this is your operational amplifier. Now this operational amplifier, it will act as current to voltage converter. Current to voltage converter, right? So it will convert this current to a corresponding output voltage. Okay, and the output voltage, it can be calculated by this formula. It is minus V reference divided by 8 multiplied by the number of bits, right? So B is your number of bits. Okay. So you can have a 4-bit DAC, you can have a 8-bit DAC, you can increase the number, right? So it is, this R2R ladder is very simple to construct. You would need only 2 precisely controlled resistors, right? So similarly, there are several advantages of this. You can read or you can search for those advantages. Okay. Now, to quickly discuss about some of the specifications of this DAC. So the first specification is your resolution of DAC, right? So it is the percentage resolution of a DAC. It will depend on number of bits, right? So whether you have a 3-bit DAC or an 8-bit DAC or a 4-bit DAC, it will depend on that. And it is calculated in percentage and it is given by this formula. It is equal to step size divided by full scale range multiplied by 100. Okay. So again, since it depends on the number of bit, so if you have larger number of bit, let's say a 10-bit DAC will have better resolution than a 8-bit DAC. So if you increase the number of bits, you can detect smaller signal or your resolution will be much higher. Okay. The resolution of camera, if you zoom into the picture, you can zoom up to a very great extent, right? So you can even see the smaller detail, right? So similar to that, resolution means you can detect smaller changes. Okay. Now here is a numerical. I'll quickly go through it. So a 10-bit DAC has a step size of 10 millivolts. So the step size of this DAC. So basically, if we have an analog signal, what we do is we kind of divide it into smaller steps like that. Okay. So at each and every time duration, we will take a sample, right? So you can imagine it as a step. So the step size of this DAC is 10 millivolt, and you have to determine the full scale voltage, output voltage. So since we are given with the number of bit, so the step size we can calculate, right? So it will be 2 to the power n minus 1, and that comes out to be 1023 number of steps. Each step we are given that it is of 10 millivolt, right? So the maximum voltage or the full scale voltage that we can detect, it will be, each step size is 10 millivolt, you have 1023 number of steps. So if you multiply them together, you'll get 10.23 volts. And you can calculate the resolution. So resolution is your step size divided by the full scale reading. Now resolution for DAC is different, the formula is different, and for ADC you have a different formula, so don't get confused, right? So it will be, if you calculate it using the formula, you will get 10.23 volt. The next specification is accuracy. So accuracy, it would mean different things for different equipments or different people. But most commonly, accuracy, we can specify accuracy based on two of the specifications. So one is your full scale error. So full scale error is the maximum deviation. It is the maximum deviation of DAC's output from its expected value, right? So overall, what is the deviation from the ideal value which it should be and whatever you are getting? So that is your full scale error. It is expressed in percentage. Linearity error is the maximum deviation in step size from the ideal step size. Now since you have an analog signal which is changing, so you cannot fit the same, or you cannot use the same step size. Sometimes you may have a little higher step size, sometimes you may have a smaller step size, right? So it is the deviation from the ideal step size which it should be. Ideally we would assume that the step size should be the same, but practically it is not, right? So that difference is your linearity error. Okay, so again you have a question based on this. So you have a DAC which has an accuracy of plus minus 0.01% full scale and has a full scale output of 9.375 volt. Okay, so accuracy is given as well as your full scale output is given, right? So I mean, it's a very common thing. So if you are asked to calculate the full scale error in the output, so what we can do is we can just multiply them together, right? So accuracy will be approximately 0. plus minus 0.9 millivolt. So what it would mean is the output of your DAC may be slightly off, or it may be different by as much as 0.9 millivolt. You may expect a different value and that difference will be 0.9 volt, plus or minus. Okay. Here you have another example. So a 4-bit DAC has an expected step size of this, 0.625, and has an accuracy of 0.01%. So you have to calculate the linearity error. So since we are given with the step size, we can calculate the full scale value, right? Number of bit is also given. It is a 4-bit DAC. So using this formula, we can calculate the full scale value, which comes out to be 9.37. And for calculating the accuracy, you are given with the percentage, you multiply them together. So you will get the linearity error. Okay. So again, this would mean that your step size could have a difference of plus or minus 0.9 millivolt. Okay. The last set of specification is your offset error, right? So ideally the output of a DAC should be 0 volt when all the binary inputs, they are 0, right? So if you have a DAC, you have like multiple bits, right? So your output voltage should be 0 when all these bits are 0, 0, 0, right? But practically you would get some voltage, very small, maybe plus some voltage or some negative voltage you would get, right? So this is called as offset error. Now what we do is we connect a voltage source depending on this offset error. So if you are getting a positive voltage, we connect the same negative voltage to cancel that voltage out, to nullify the voltage, the offset error. Okay. And lastly is your settling time. So the operating speed of a DAC, it is given by its settling time, and settling time is the time required for the DAC's output to go from 0 to full scale value. Okay, when the binary input is changing from all zeros to all 1. So basically when your inputs, the binary inputs, they are changing, right? When your inputs, maybe they were 0, they are changing to some different values, right? So it is the time taken for your output to change from one voltage to another when your inputs, they are changing, when your binary bits, they are changing. So generally it will take some time to change the output voltage, right, from V1 to V2. Generally it is 50 nanoseconds to 10 microseconds. It's a very small time, but it does take some time to change the output according to the input binary bits. Okay, so this is your settling time. So this should be all for today's lecture. So basically we have covered all the fundamentals of your digital electronics part, and in the next class we'll continue with we'll discuss some of the avionic systems, right? So you have so many different systems. We are going to take one of them at a time, and then we are going to discuss the different type of component or subsystems which are there within that.